Hello, everyone. Welcome to the BE Introduction to Graph Neural Networks tutorial. I am Alina Lazar. I'm a professor of computer science at Youngstown State University, and my co-presenter is Shengyang Yu from Berkeley National Lab. So our tutorial will have two parts. During the first part, we are going to talk about graph representations and the different graph level tasks, node, edge, and graph level. We'll give examples of simple graph neural networks, and we'll talk about some other architectures. During the second part, we'll have like a hands-on tutorial. Some simple graph networks will be introduced, and we'll have a notebooks about node classification and edge classification. So before we start, we also have a GitHub repository where we have the Python notebooks with the examples we are going to go through. And you can also find the tutorial slides on this GitHub. Okay, and I would like to invite you to go to this website, and we are going to have Q&As, so you can submit your questions, and we can go over them during the tutorial. Okay. Okay, so everyone has heard about the success of deep learning in the recent years. Deep learning has revolutionized many machine learning tasks in computer vision, in image processing, even in gaming. And the factors that contribute directly to this are like many of algorithmic innovations in machine learning. We are collecting more and more data, and also the computer platforms have become better and faster. And some of the hardware accelerators like GPUs contribute to the speed of training and inference in deep and machine learning. So in order to make these, to implement these revolutionary ideas, we need tools for data representation. So in many problems, the data can be represented in the Euclidean space. Like for example, for multi-layer perceptrons, the data can be just like a matrix or a vector. When we do image recognition or image processing tasks, data is an image or a grid. That's the input of a convolutional neural network. Or in the case of recurrent neural networks, data is a sequence, a time sequence. But what if the data that you have to work with doesn't come from like this two-dimensional size grid, and instead it comes from a non-Euclidean domain, and it has dynamic size, irregular shape, or sparse density? In that case, tools like graph neural network can capture the complex relationships between objects and interdependency much better than any other representations. So again, this graph representation can capture not only the complex relationship, but it is dynamic, has a powerful expressiveness, and it captures the relationship between the objects or the interdependencies. There are many successful applications where graph neural networks have been already applied, like drug discovery, physics simulations, particle tracking reconstruction from high energy physics, and learning from a knowledge graph such one built on the data from Wikipedia. So graph neural networks are just a subset of deep learning methods. They can provide useful predictions on this type of representations that I just mentioned, and I will talk in more details in a minute. And are one of the fastest growing and most active research topic. As you can see, they were mentioned in the first talk today and in many other sessions at this conference. Okay, so at this point, I would like to know a little bit more about your background, like what is your knowledge about graph neural networks? So you can use your phone and get the QR code to answer this question. We don't have a right or a correct answer here. There is no correct answer, it's just a survey. Okay, so it looks like most answers say, I know deep learning, but I have not worked with graphs. So you are in the right place because this is an introductory tutorial and we don't assume prior knowledge. Okay, so there are many problems out there that can be represented as graphs in several application areas, such as proteomics, image analysis, scene description, software engineering even, and natural language processing or text. The simplest kind of graph structures will just include nodes and links between the objects. But in several applications, the information is going to be organized in more complex graph structures that will have additional features as node or edge attributes. So one very simple example from image processing or image classification is this example that comes from the well-known NIST dataset, and it converts the pixels in the image into like super pixels, and that provides the graph representation on the left, on the right side image. So here, the machine learning task is to classify the image into two subcategories which represent each digit, each digit, yes. And that can be done with a simple graph neural network. Another example which represents text as graphs, here we can digitize the text and associate indices for each character or word, and then represent the text as a sequence of these like small tokens. And then in order to create like just a simple directed graph, we can have each word is a node, and the connection is an edge where the edge goes from the word to the word that follows in the sequence. And that's exactly what you can see in this example here. So in both these examples, the image and the text, the adjacency matrix that we are going to mention later is just a diagonal line because each word only connects to the prior word and to the next one. Now, again, as I mentioned at the beginning, images and text are homogeneous, so they can be represented with two-dimensional structures. But moving on to more complicated structures, we can talk about or look at molecules as graphs. In this example, the number of neighbors to each node is variable, so it gives you like a more complicated structure. So molecules are in general harder to phrase in using other representation than a graph. So molecules are the building blocks of matter and are built of atoms and electrons that are connected in the 3D space. And the different pairs of atoms have bounds at different distances. And these are like represented in the graph by the edges that connect them. Another example comes from social networks. So social networks study the patterns in collective behavior of people, institutions, and organizations. The graph representation so the models have people as nodes, and then their relationships are the edges. Again, unlike images and text, this type of graphs do not have identical adjacency matrices or representation. And this type of graph can also be used in recommendation systems. And another graph or representation, another example related to this type of social network recommendation type of graphs is the citation network. This example here comes from the patterns of citations in German political science. And this will actually be the input on one of the examples in the hands-on session, more precisely the node classification part. There are still other examples of graph representation like objects or their relationship in visual scenes, machine learning models, programming code, computer networks, time series, mathematical equations, even different physical phenomena. So we can look now in a little bit more details on how to represent graphs or how is this mathematical structure. So a graph is composed out of nodes and vertices, and also they have a set of edges and links. We can have like undirected and directed graphs. The example up there with 5 nodes is an undirected graph. And so these graphs, as we can see here, the edges are represented with a list of pairs of nodes, but another way to represent the the edges part of the graph is using an adjacency matrix, which has a 1 for every 2 nodes that are connected together. Now, when you have very large graphs, the adjacency matrix can become very big. So using a list of edges, it's probably more memory efficient, but there are also efficient implementations of using the adjacency matrix in a sparse way. So connecting now, going back to the machine learning concept, so we want to find a way to use the graph representations using machine learning and deep learning in order to solve problems for these more heterogeneous representations of applications and problems. Machine learning is the scientific field dedicated to the understanding of building methods that let computers learn. It's part of the artificial intelligence. And the algorithm are run to train models on sample of data or training data in order to make predictions or decisions that otherwise could not be guessed. Just to give the very simple example of image recognition, a convolutional neural network can take images as training and output like a classification. In this case, do we see a cat or a dog in the presented picture? Deep learning, on the other side, means training a neural network to learn and identify features in the training data. So it can identify similar features and give an appropriate output. Deep learning is basically neural network architecture with multiple hidden layers. So what type of problems or tasks can we solve by using graph structured data? So we've seen all the components that go into a graph. When we represent the application data using graphs, there may be different types of groups that we can use to come up with the machine learning task. And they are basically divided into 3 groups: node level, edge level, and graph level. So for the node level, the classification problem will divide or will predict a class, most of the time a binary class for each level, for each node in the graph. And for edge level, it will predict 0 or 1 for each connection. And in terms of the graph level, the classification goes on the entire graph. And it's not just, it can be, in addition to binary classification, multi-class classification or even regression. Okay. So first, we'll take a quick look at node level tasks. And the simplest example comes from this problem. It's called Zek's Karate Club. And this data set is a single social network made out of like 40 something people, individuals that belong to the same karate club. And as the story goes, there is a quarrel between the instructor and the administrator, and that creates like a friction in the club, and people will go with one or the other. And so we want to, the classification output in this case is to which group each individual belongs. In order to, so we can definitely build a graph, and then depending on the connections between the individuals are based on their outside of the club interactions and how many interactions they have outside the club. Based on this link feature, we can classify the nodes into two groups. So that's the idea behind node level classification. And you can kind of see on the right-hand side graph, we have red nodes versus green nodes. Then the second type of classification is the edge level. This is the most common edge level task is known as the link prediction and can be used for making recommendations. So if you have a given graph, you want to predict if there will be or should be an edge between two nodes. So in social networks, this translate if social media companies should propose a new friend to you, or if they need to make a recommendation, or if there is a future citation from one paper to another. And just to do like basic binary classification, we should have like a 1 if there is a link, and the network should predict a 0 if there should be no link. This type of link classification can also be used on identifying the relationship between objects in an image. This can be used to predict the relationship between the objects in a scene. And in addition, I just want to mention that even if the edge level and node level are described as two different problems, actually an edge prediction task on a given graph G can be phrased as a node level prediction on the graph's dual. So the dual is like a way to convert nodes to edges and edges to nodes. So if you solve the problem and you are getting very good results for node classification, you can use this dual to also use it for edge level tasks. And then finally, at the graph level, the object here is to classify an entire graph instead of just single nodes. So given a data set of multiple graphs, we want to classify individual graphs into, based on their properties, into classes. One of the most typical tasks in graph classification is molecular property prediction, and this is actually a regression task. And there are not just one, you can predict multiple properties. And so this is based on the atoms being connecting together in the graph with all these bounds between the different atoms. So the goal of graph neural networks is to optimize transformation of all the attributes in the graph, including nodes, edges, and the global context, and also to preserve the graph symmetries. The graph nets architecture was actually introduced by Battaglia in 2014, and this architecture unified the different previously proposed architectures. The most important concept in graph neural networks is the message passing framework that was proposed by Gilmore in 2020. And in general, graph neural networks adopt graph in, graph out architecture, which means that the graph and the connections stay the same. The simplest example of a graph neural network includes information about the nodes, the edges, and also about the global context of the graph. And here we are learning new embeddings from all these graph attributes like nodes, edges, and global. But at the simplest level, there is like no information about the connectivity used during the training algorithm. This type of GNN uses a separate multi-layer perceptron for each level. So one for the node level, one for the edge level, and one for the global level. And as it is like common in deep learning, we are just like, we can stack the GNN layers all together. So the simplest task is to make, as I mentioned, binary predictions on nodes. And in order to do that, for each node embedding, we can apply a linear classifier. Again, the example we are going to look at in the tutorial is the Karate Club example, where we use the number of meetings between the people to determine the alliance to the two people in charge. So in order to make predictions by using the message passing framework, the framework works in three steps. So for each node or edge, we can pass messages to all their neighbors around. At the second step, we aggregate all the messages via an aggregate function or like a reduction function, where we can use sum, mean, or like a min or max. And then at the third step, we concatenate the messages that are passed through an update function, usually learned by the neural network, in order to update all the embeddings and relevant features. So then the question is, depending on what type of features or attributes we have, we can, by using the message passing, we can pass features from nodes to edges and from edges to nodes. So in this example here, we have edge attributes, but we want to make node classifications. And by using the message passing, we can send the edge information and pass it to the nodes for the final classification. So as I mentioned, this can be done from the edges to the nodes, from the nodes to the edges as well. And we can also do it from the nodes in order to do the graph level classification. So the next topic I'm going to talk about is how to use this message passing in order to build a graph neural network for a specific prediction task. We already saw the node level predictions, the edge level predictions, and the graph level predictions. So the message passing in the end it will so for the node level predictions, we use all these like embeddings and aggregations to classify nodes into 2 or more groups, or to make edge predictions where we classify the edges, or to classify entire graphs. All these different level predictions can use the information from both nodes, edges, and less frequent, but also graph level information. Many improvements on these simple concepts have been done in the last couple of years, starting with graph convolutional networks. These are very similar to the convolutions used in image processing, in the sense that you have filter parameters that are shared all over the locations in the graph. Graph neural networks, mostly graph convolutional networks, rely on message passing methods. In addition to GCNs, there are the graph attention networks, or GANs, where this type of models weight neighbor nodes with edge weights before the aggregation. And there are also many other architectures. If you are interested, you can check the link, the PyTorch link we posted here. And so related to some of these newer architecture and newer ideas in graph neural networks, many times graphs for applications, for many applications, this type of graphs can become very large, and it's hard to fit them in memory in order to be able to train good models, efficient models, and very accurate models. So one idea is to, especially for graphs that do not fit into the main memory, is to sample the graph and just use subgraphs in order to train the model. The way this is done is by taking a collection of nodes, and then for each node in the subgroup, you also include the one-hop neighbors and the two-hop neighbors, which are the connected neighbors at one step and like at 2 steps or even 3 steps. This is really interconnected with like how many layers of message passing you have in the network. And also a different idea, even if your graphs fit the memory of your computer, you can use mini batches that, or again, subsets that are constructed in the same way. And by using mini batches, your model will converge faster than when you use the entire graph. Okay, it looks like we have a couple of questions. The first question, how do you determine the correct decomposition of your problem onto node or edge or graph level tasks? So in other words, like how you have an application or your problem, and how do you come up with the correct representation, or how do you even come up with a representation for your problem? I think that you can look at what other examples or how people are solving problems. And when you look out there, most examples use node classification. So you can try that first. And however, if your problem comes from like social network, or it has any type of link that you need to classify, that will be an edge classification task. And the second question here is, how is a node different from an edge from a graph level in the way they are represented actually in the GNN message passing?
Well, the nodes are basically assume this question is asking how the nodes and edges are represented in the GNN, in the graph neural network. If that's the question, so nodes basically presented as a matrix where each node have their own features as a column, and then each row represent a node. As an edge that represented as an edge list, a list of your two nodes that get connected. So indices of the node indices as a way to represent your an edge. That's how we represent a graph in a graph neural network. For the input.
Yeah, so we talked about the edge list and the adjacency list. These are used in the actual implementation, and you first need to build your graph in terms of deciding which are your nodes, what features or attributes you want to include, and build the edges in terms of like the adjacency matrix or the list. And that will be the input into the GNN. Okay. So in conclusion of the first part, graphs are really powerful and rich structures that have strengths and challenges. They are different from the other types of data that are most common in deep learning, like images and text. But it's a great opportunity to apply it to a wide variety of new problems and on using complex and large data sets. Sometimes it's difficult to come up with the right problem representation, as we've seen even in the questions. But important practical problems can be solved, and there are many open research areas where data comes from like a non-Euclidean type of patterns and relations. And it's much better to, this type of representations can be used successfully. Okay, so for the second part of the tutorial, Shangyang is going to go over and talk about another GNN application that he's working on, and he's going to go over the hands-on examples. So if you want to follow along, you can activate your training account based on the information posted here. Okay.
Thank you, Alina. So maybe we pause here for a few seconds for you to set up the account. And yeah, if you have that set up, maybe, do you think we can create a live poll?
Right now?
No? Okay.
To see if
everyone has an account.
Anyone needs help?
Okay, if you have like your account set up, then we can move on. Can you raise your hand if you have your account already? Oh, wow, okay.
I think you can start.
So here I will talk about some of the graphs that we're going to use in the hands-on section for our tutorial. We basically have 3 tutorials, 2 focused on the node classification, and 1 focused on the edge classification. The edge classification example I was taken from the application that I'm working on for the high energy physics. A short introduction myself is that I'm a computer system engineer at a Berkeley lab, and I work on the interplay between particle physics and machine learning. So currently, my research is using the graph neural network to solve some pattern recognition problems in the particle physics. And that's our third example in the hands-on tutorial. Yeah, a few words about the high energy physics. So the device that we're working on is called a Large Hadron Collider. It sits on the border of Switzerland and France. What it does is that this collider things, it accelerates one proton beam as a clockwise and another proton beam anti-clockwise, and then they will meet and collide at 8 points. In each of the points, we have an experimental detector to detect what comes out from this collision. Those detectors are normally very large, 10 meters high, and the experiment I'm working on is called ATLAS experiment. The scientific goal of this experiment is to explore the elementary constituents of matter. So try to understand what matter is made of, what are the elementary particles that cannot be break down any further. And we also study the fundamental interactions between them. So in order to achieve this scientific goal, it's very important for the physics programs to reconstruct the particle trajectories. Because from these trajectories, we can infer the charge of the particle. We can also measure the kinematics of the particle. So the left-hand side just shows you a so-called event display. That's what this information in the information we have recorded in our detector. If you look at these red lines, those are muons. Muon doesn't interact much with our detector. It's mostly escaped, but it will leave a track in our detector. That's how we know it's a muon. And in the innermost, you have this yellowish curves. Those are trajectories left by the charged particles. And you see that there are many such curves. And what we were given from experimental point of view are a couple of dots connected in the detector. And it's the objective of the scientist to figure out which particle leaves those dots in the detector. So that brings to this innermost detector that we are talking about. And this is I think we had this Kaggle challenge in the machine learning for particle tracking. I forgot to put a link here, but the idea is that you have a list of points in the 3D space as shown in the bottom plot. And the objective is to connect those together in order to form a trajectory. In our hands-on tutorial, we have simplified a little bit in the sense, instead of giving you a point cloud, we'll give you a pre-made graph. So we take the true connections and add some noise, and then we will construct a graph neural network to separate the true connections from the fake connections. Then that's become a age classification task to solve some binary classification problem. It's a very challenging problem because although I'm here in this bottom plot, I only show you 10 tracks, 10 particles. But in reality, we're dealing with 10,000 particles, like something on the top. And it's just impossible for a human to label all those points coming from the same track. You have to use some smart algorithm to do so. Yeah, so that's where this graph neural network comes in. You have a graph at the input, and that goes to the graph neural network. This graph neural network can be any type, can be different variations. In the end, the graph neural network will assign a score for each of the connection, a score between 0 and 1. And what we can do is that we can put a threshold on the score, so only those true connections are left, like displays on the right-hand side. So that's basically the objective of the third example for age classification. For the second example, we have this Cora dataset that Alina just introduced for the citation work. Here, you only have one graph, and this graph has 2,708 nodes. Now, each node represents a publication, and among those publications, there are about 10,000 links. Each link represents that the one is citing the other one. So they have a citation happens between the two publications. I think this can be modeled as a directed graph, in the sense that if a publication 1 is referring to publication 2, you only establish one connection, directional connection. But I think the graph we had is undirected, so long as the A citation there is on age. However, the task is really classify each publication into one of the predefined categories. Right. The challenge really for this problem is that only 5% of publications is labeled, and 95% publications are not classified into any category. We don't know, and that's the job for the graph neural network to learn a pattern in this graph, so to predict the category of the 95% of the particle in this data set. And in our example, actually, we will compare like the performance of the GNN with respect to a simple multi-layer perception. Yeah. The first example you have to encounter, sorry for I do the reverse way because the third one is connected to my field. But the first one is really an exploration introduction to the graph representation that in practice, how do you do that in the in coding in Python. And this is a very small graph, and the objective is very similar to previous example. You basically do the node classification to classify the character member or carbon members into one of the four predefined communities. Yeah, that's about the graphs that we're going to use in the tutorial. And the framework we are going to use is the PyTorch geometric, it's PyG. We acknowledge that there are many graph neural network frameworks. It really depends on your own taste. If you are like a Julia person, you may want to use a geometric Flux Julia. Or if you are like TensorFlow folk, I think the library developed by GraphNet and Spectra, yeah, that will be very nice candidates. If you like PyTorch, I think PyG and DGL are also good candidates. But in our tutorial, we just use the PyTorch geometry. Well, it's for a couple of reasons. I think it's built upon on the PyTorch, and it's pretty easy to write and train the GNN for a very wide range of the applications. And recently they developed this so-called torch quiver that help you to run the training on multiple GPUs without much of boilerplate setup. Unfortunately, in our tutorial, we did not explore the multi-GPU training, but I do think in your training, a counter should have access to GPUs in per matter. That's the NVIDIA GPU A100 with a very large memory. The other part that PyG provides is they have predefined graph neural networks. Those popular models, they have implemented them in a standard way. And they also provide like predefined data set that you can use. So for example, the first two examples, you don't need to download anything. It automatically managed. So without further ado, let's get started with the hands-on session. So the idea, you will set up this. I will not set up like here, but if you have any question, just you can raise the hand so we can we help you to dig out the problem. In the meantime, I will just walk through that we have pre-compiled notebook in the GitHub. So far that everyone has an account in NERSC and was able to request an exclusive GPU node. Oh, you have? Okay, so which one did you choose? Did you choose the GPU node? Exclusive GPU nodes, you get a timeout. If that, can you then try, how about, yeah, in this way you can try the shared CPU node, although it's not really like ideal. Yeah. So who has also problem in accessing the GPU nodes? 1, 2, 3. Well, it's all like timed out basically. If this timed out, I would suggest we use the CPU node for imprimatur.
Yeah. So, Johannes.
Or Johannes can help us a little bit here.
Maybe I'll walk up to the microphone so then people can hear. If you look at that screen, on the far right, you have a column called configurable GPU. If you select the top column, so a configurable GPU on Perlmutter, then you should see a screen that lets you specify a bunch of things.
We have it on, I think, on the next.
Yeah, okay, yeah, if you select that button, and next slide, please, yeah.
Okay.
So there you see the screen. You need to make only 3 changes. The top row, you should enter ntrain 8. It's sort of a drop-down menu. The reservation name is also from a drop-down menu. Select SIME, oops, I think I might have spelled it wrong. No, yeah, I spelled it wrong on the slide, but not in real life. SIME intro GNN, and then select a time underneath that. I usually say 2 hours. The reservations start 15 minutes before the tutorial and run for 3 hours. So you want your end time to fall within the end time of the reservation. So if you do that, then you should skip the queue if everything goes well. Yeah, 120.
Yeah, you put 120 minutes.
Maybe put 60 just to be safe, because we're already an hour into the tutorial.
Okay, so everyone try this configurable GPU in Perlmutter. So next is after you're doing that, well, you connected the first 2 bullets, third 3 bullets. You can click on this Git menu and do clone a repository. This is a repository for the tutorial that includes the data as well. And that should like make you create a local folder called intro to GNN. They can basically click into that folder, and on the right hand side, yeah, then you can open, for example, the first notebook. You still on the GPU queue?
Yeah, same here.
Did you put 60 minutes maybe?
No, I put 120 before y'all. I mentioned the 60. Should I like go back?
Let me just check. Right, okay. We'll probably just wait a bit. Yeah, let's wait like a few minutes so it's going to load up. It's loading. You can also, yeah, we should also be able to use Colab. But for the third example, I did not test it exclusively in the Colab, but we should try that. No, unless you go to the stage. Maybe we need Change it to a collab.
You just need to. Oh, yeah.
Here.
Oops.
Attempt number 3. Ooh, that's loud. Sorry. I've just confirmed you can use the reservations if you set your time limit to 60 minutes. It just takes a moment to connect to, once the server spun up, it will say the server's been spawned and it's waiting to connect. But that means you've skipped the queue and the machinery just needs a moment to connect you to the node.
How long?
And it seems to be taking a long time because we're having some technical difficulties over at NERSC.
Kind of hung up, and I don't know how to stop it. And
No, it's the wait. Yeah.
Yeah, because
please go back.
yeah.
No. Huh? Yeah, you can. Yeah. Well, normally just wait until it shows up. I don't know why it's so slow, but. Okay. So if you try again, I think if you so again, we do help people get the allocation, or it just take time for the system to create an access. Yeah, it's cloning, so yeah. Maybe we can sit together closer. Yes. Oh, great. Yeah. If you click the menu, file, yeah, file. Yeah. Oh, sorry. Git.
We said change it to 50.
On the repository.
Yeah.
Put that
PyTorch.
repository link.
PyTorch 1.9.
So let me just show the link again.
So when you get in, select the kernel PyTorch 1.9.
Right, once you're in, there is on top, there's small words, file, view editor, you click the Git. And there is an option called clone the repository, and where you can put the link to the repository. Who got allocations working? Okay, I have a few.
Looks like half.
Okay, Pramod, I really having bad time today.
Yeah, so you really need the GPUs, right?
I think it's CPU is okay. We are not so extensive in terms of computation.
Right. So for the sake of time, I would recommend that people fail over to the GPU. Is it
CPU.
CPUs?
Okay. Okay. So then in this case, yeah, maybe we can just get started with the CPU node where if you go to the main page again, instead of configurable GPU, we can do shared CPU nodes, and that hopefully can give us quickly give an access. It's just like your training will not use GPU, but mostly depends on CPU. Shouldn't matter much. Okay. So for those who did not get the GPU node, let's use CPU node by clicking this this parameter CPU node.
I think you can start.
Okay. You assume like you have the Jupyter setup, and then also clone the repository to your local directory, and we can look into the first example. I mean, yeah. So wait, let me just jump into the first example. So this example uses a hierarchy club dataset, and the first entry you see is that you just import the torch, where you will get most of the torch libraries, and it's important to check the version of the torch they're using, and the tutorial today is mainly based on torch 1.9.0. This is like because this kind of machine learning packages or frameworks are evolving very rapidly. Some of the API may change from time to time. So it's important to know which version you have in order to have reproducibility. We also write a helper function to visualize the graph, basically to plot the nodes and edges. You can ignore that function, just run that cell. So the neural network, the graph neural network we are going to use is a simple message passing neural network. Okay, I will skip those mathematical terms as Alina already introduced you this message passing, how it works in 3 steps. But I want to show you how that gets implemented in the framework. I will not show you like a very detailed, but from user's point of view, if you want to implement a graph neural network, how it looks like. So first, let's look at the dataset. This dataset is already prepared by TouchGL metric. You just like from here and then import the dataset and create an instance of the dataset. It automatically downloaded for you. You see that PyG as a framework to study the graph neural network, it has predefined features in order to represent a graph. Okay, this is just their definition. It's not set to stone. If you move to another framework, this representation may change. First of all, you can see the length of the dataset is 1, means that there's only one graph. Let me just zoom further since we have space. And this number of features. So here, the number of features are really associated with the features of each node. Okay, and each node have 4 classes. So this is their predefined features. In practice, you can define any attributes associated to the data set. You can do it by yourself. You can just assign, say, dataset dot something equals something as assignment. But this give you the dataset, and next cell is that you look at the graph. So you only have one object. You look at the first object, and you can find out how many nodes in the graph. That's like you want to inspect the graph yourself. Of course, you want to know how many nodes and how many edges. And in the graph theory, people define the node degree as the number of edges divided by the number of nodes. And they take the average, right? Training, so here the training mask is that for the dataset, some of the nodes and edges you want to use for training, some of them are used for testing. So this just give 0 if that used for testing, 1 if that used for training, and that's that. What's particular is that this is a predefined convention. If you stick to this one, is that you have to have an X. X is the node feature matrix, where each row stands for a node, and each column stands for a node feature. In our case, we have 34 rows, means that we have 34 nodes, and each node is a club member. And in the column, we have 34 features, and that means that we have each club member is get associated with 34 features. In context of this data set, is that each row represent each other club members, actually including himself. So that's the data set that you want to define on X. If you want to define a data set yourself, you need an X to represent so-called node features. A graph must have a node. Now, graph may also have connections, so have the links. That's represented as age index. That's in the dimension of 2 times number of edges. So when you see 156, it means that in this graph formed by 34 club members, only have 156 connections. And the other object called Y, normally that's your objective. That's the goal you want to achieve. That's the truth labeling you have. Here in the dimension of 34, that's represent each node that belongs to one of the 4 communities. So each one has a number associated with that. So this is with dimension 34. This kind of dimensionality analysis in machine learning are very useful. That gives you a sense how those metrics are getting multiplied and how the information are getting laid out. But in the context of the graph neural network, you need to pay attention is the X as the node feature and age index as the connections in the graph. Okay, so once we prepare the data set, we can visualize it using the predefined function we have. You can play with it and change the different colors. Basically, different color represents, I think, different community. Let's directly jump into this vanilla graph convolutional network. Okay, so how we implemented this message passing step for the graph neural network. So first of all, we need some building blocks. Those building block neural networks are defined in this initialization function. And the message passing is done by using those building blocks in this forward function. Okay, you see these kind of operations, convolutional 1, 2, 3, can be any building block you want. Could it be a convolution, or could it be a attention, could it be other modules you have. There are a variety of these kind of tools. You see that in this category called torch geometry.nn, they implemented a couple of graph level networks that you can apply, and those are your building block. In this specific example, we take this convolutional building block. Let's say we don't know what's inside. That's fine. If you are interested, we go to this this web page, torch geometric. I go to here and then look at their documentation, right? And the convolutional layers or like different models and such to understand the detail and see what are the options. But for our case, we can use it just now as a black box. So we specify the input feature and output feature. a number of output features, and we connected them sequentially. So you look at this. So we're acting on the X, which is the node features, and the X. So basically, once you have these two information, you are putting the original graph, and you get a hidden node representation. And now your graph is changed. So graph structure is the same, but each node has a new representation as an edge. And then you can put some nonlinear function and act in this graph convolutional information again. And this time the message passing what happens again, right? In this graph convolution network. And you can do this many times. In our case, we do 3 times with a different graph convolutional layer. In practice, you can also put the like 1 convolutional layers, but you have to figure out the dimensionalities. And in the end, we're using the linear component to classify each node to see which community it belongs to. So that's like overall description of the graph convolutional network. Okay. The way to use it is just create this instance of this class, and acting on the original graph, you get hidden node features. You can then you can train it with some binary. I think here we use the cross entropy loss as the objective, and use a Stochastic Adam optimizer to optimize the loss function. So these are like typical boilerplates you have in the PyTorch models. And if you keep training it, you see that those groups are correctly separated into different values, different representations. So different communities go to like club members belong to the same communities are classified closer. So that's basically the very simple graph convolutional layers that we just built and applied it on a small graph that have 34 times 34 dimensionality. Any questions or comments? Please go ahead. Yeah, I'm doing it now. Oh, I don't know how to do that. Wait a second.
What do you want to like go for?
So the question is that what's the train mask in this specific data? Because as I said, the train mask is to select the data you want to use to do the training, and then for some, you want to separate the data into training and testing, so that you are not biased by a training, or as a way to determine if the model is overfitting or not. The train mask is to down select your data.
All the data sets in PyTorch geometric have this mask, which is like an array of 0 and 1s, and you have 1 for the nodes that you are going to use for training and evaluation and testing. Like all data sets have like 3 groups. But if you create your own data set, you will have to make your own mask or randomly select and break the data.
Yeah. Okay.
Oh, there is yeah.
Right. I guess the question is that can you do layer normalization and drop out in the graph neural network and some other techniques? That's a very good question. The answer is yes, and you can do it in various places. For example, when you update your node features, you can use multi-layer perceptron plus some layer normalization or dropout in order to prevent some overfitting. This can be like one group of neural network acting on your node features. Similarly, when you are updating your edge features, you can also do that. You can even insert this building block into message passing step. Those, let me see, conventional neural networks can be readily used as the building block in the graph neural network. Because in the end, as Alina's talk has shown, the simplest GNN is those building blocks acting independently to node level features, edge level features, and graph level features. What makes GNN more attractive because you can pass the information from node to edge, edge to node, so-called biased relational bias composed by your graph structure. This kind of structure doesn't prevent you to use in those building blocks like layer normalization, batch normalization. Okay, I hope like you have learned the example in Perlmutter, either with the GPU or without the GPU. Let's move on to the next example, where you have Lazar. We will do the same exercise in a sense to visualize the data, have a sense of the data, what the graph is, and create a graph neural network to do the task. Yeah, I said this data set we have is for citation work. Again, the data set already exists in the Python geometric, and just imported it and create an instance. Say you want to use Cora citation data set, and we can do the old drill that I have seen in the previous example. There's only one graph, and this amount of publications, the links are also introduced before. So I will not spend much of time on this data set, but I want to highlight that the training nodes with only 5% of the publication are labeled, and the objective of the GNN or machine learning is to classify this publication into one of the 7 categories. So it's like classification, multi-class classification task. Now, of course, we can look at the publication by itself, right? In this metric, this shows you there are 2,708 publications. That's the number of nodes in the graph. And each publication have this 433 features. In principle, you can put this into a machine learning model like a multi-layer perceptron and make a prediction to see what this each node comes in which category. That's responding to a Y value. That's exactly what we have implemented in this as MLP. It's just two MLP layers with activation function of ReLU, and we also add a dropout of 50%. And after you train it, you see this loss goes down rapidly at the beginning, and in the end, it stopped going. It also goes like very, very low, but this only shows you one side of the story because this only you trained it on the labeled publications. When you apply to those unlabeled publications, you found that this accuracy is not so great. It's only 57%, which partially because this MLP only uses a publication by itself. It doesn't use the citation information. We know that two publications, if they cite each other, it's most likely they're on the same field or on the same category. And this kind of relational bias was not used in a multilayer perceptron. Instead, we can impose this kind of bias into a graph neural network. That's where this is the same graph neural network we have shown before. It's a graph convolutional network. It's only have 2 layers, and we do the same training. You do see visually they are much better separated. And if you test it with the testing data, the test accuracy increases dramatically. Of course, we can further improve this one using different variations of the graph architectures. Okay, so this goes a little bit fast. I don't know if any questions, or is anyone managed to run this example in Perlmutter or Colab? Colab works. Okay, that's the way to go. So I think as like for your curiosity, you can actually change this convolutional layer to be different layers, like graph attention module, and to see what kind of results you would get out of the classification task. Yes. So the question is about what's inside the convolutional graph convolutional layer or the building block. So this is a typical message passing step where the information is sent from. So we have a publication in question, that's our node in question, and it will connect the information from the nearby nodes. Depends on if this nearby nodes is get cited or not. So if there's an edge between the 2 nodes, means that there's a citation happens between the 2 publications. So it will gather those neighboring node information into this node in question. And because you have so many neighboring nodes, and its number of neighbors for these nodes in question can change from node to node. So we also apply an aggregation function. For example, we sum all those features together and then concatenate feature neighboring information with the original publication information together. So that's what the convolution is doing. So in the end, it will give you a new node representation. So that's where this hidden channel comes in. That's what that stands for. It means that, let's say in our specific case, we have each publication have 1,432 features, and that will get condensed into what's the number of the hidden channels? I don't know. Yeah, into let me see. I should be able to find it here. If we did a print, yeah, into 16. So the original 14, this amount of feature will be condensed into 16. But this 16 is calculated based on the publication itself and the neighboring publications or publication get cited. That's a good question. Yes. Right. So that's the aggregation. So in this context, the aggregation is the sum of the neighboring information. Let me see the equation carefully. So in this way, I think in this formula indicating that you only use, yeah, you also treat yourself as one of the neighbors. So it's not a concatenate, sorry, it's not a concatenate in this case. It's basically aggregate everything together. Yeah. Okay, very good question. Anything else? Anyone? Okay, then move on our third example that have a different objective. And for third example, I actually hacked a bit in terms of data. I actually have a copy of the data in the repository. You cannot do the torch dataset and import torch dataset and done with it. Cannot. This I ran in. Okay, this is with a different torch version, but I think this also works on 1.9.0. But the torch geometry version should be this latest one, 2.0.4. This is what we have been working on to do the edge classification with the so-called interaction network. Again, we want to visualize the graph first. So we have only one graph. This one graph responding to a collision, physics collision. And then we visualize it in a different way. So here I just randomly select 10 tracks and visualize them. So because each of the dots are represented in a 3D position, I only plotted them in two projections. One is in the view XY and the other in the view of R and Z. And you see they are mostly like straight lines in the R and Z. And depending on the kinematic, this can, in the XY view, can be slightly different. But this is only 14 track. Your input is those dots, and you want to connect those together. But what if you view all those edges? It will become like this, right? It's just impossible to make the connections by hand. So what we did at the training input, I actually cheated. So basically I have this, I call it true graph. So you can obtain this graph from simulation. You only collect those dots coming from the same particle from your simulation. And then I randomly add connections between the nodes by the same amount that equals to the number of true edges. So then you have a graph that have some true connections and the same amount of fake connections. Then the objective of the graph neural network to figure out which edge, which connection is true, which connection is false. Then you are converting this global problem where you want to connect all the points coming from the same track into a local problem where you want to make a decision if the two dots, two nodes coming from the same place, if this connection between the two nodes is true or not. And this becomes a local problem. And still, the GNN was able to use this relational information to help make the final decision. So this edge classifier we're using have basically three components. First component, this actually is not exactly our idea. It's I think from the GraphNet DeepMind. And I find that this kind of architecture is very universal, can be used to solve a couple of problems with a similar architecture. The three components includes, one is that the graph encoder. Graph encoder says that you give me a graph with arbitrary input attributes. You may have node attributes, may have edge attributes, may have like graph level attributes, but I don't care because I'm going to encode your input into a graph that has all types of attributes. It has node attributes, it have edge attributes, it have graph attributes. Regardless of what information you have, I can always find a way by message passing to create a graph that has all three kinds of attributes. Once I have this kind of graph encoded, I feel comfortable to do full level of the message passing. I can pass the information from node to edge, from edge to node, from node to global, from global to edge, whatever you can enumerate, all kinds of things. However, as I emphasized before, we want to convert our problem into a local problem. So we also constrain our message passing to be locally message passing, meaning that our node, we only pass the information from the node to the edge and from edge to the node, and that's it. There are no global features, and we don't pass information from node to node. Although they are connected, we do not do. Only because we want to confine you sending information from this node to your neighbor, which is on edges. So that's what we did. Of course, then we first in the initial class we created some friends, some building blocks. I think our best friend is the MLP. Here you see that. Well, I did not show you the four arguments to construct the MLP, but that including layer normalization, dropout, those you can name, activation function, and you can specify how many layers you want to have and what's the layer size. And the other argument we put is this number of message passing, how many times you want to pass the messages, as shown in this diagram. And in the end, we also construct a decoder. The decoder itself is just an MLP, and this decoder only acts to the edges. And with those in mind, this is our main building block to do the message passing or interaction network. Here is the view of the edge classifier. So, is there any question regarding to the edge classifier? Okay. While you think about it, let me just show you how the training results. So to train them, you see this is still the boilerplate. So you define the binary cross entropy, and the optimizer, which is use Atom and initial learning rate of 10 to minus 3, and this the boilerplates, nothing fancy, and we train for 25 epochs, and you see this learning rate goes down very rapidly. And if you evaluate the performance, we can see that this is the model output. So the model output, well, this is before we apply the sigmoid. But you can imagine I can simply do a transformation so that the output becomes between 0 and 1. But certainly you can see that they are very well separated. The fakes are with the relatively smaller values, and the fake are true with relatively higher values. And the area on this ROC curve is just very, very high. It's very high. So it's very success, and it's also very effective in terms of computation. It performs very well in even dense environment or larger graph. And I believe that this kind of model can be readily applied to other age level classifications, and also people use it to do the node classifications. I will not dive into much of this technical part. You can have a look, but yeah, but we are glad to take some questions and comments.
There is a question here.
We have a question online. If the nodes of the graph are relabeled, so the graph is the same, but the adjacent matrix is different, does this change the output of the GNN? Is invariant? So the question is asking, my understanding of the question is that asking if nodes of the graph are relabeled, right? That in the other ways of saying it, it means that the order of the nodes in the graph is shuffled. The node 0 becomes node 1 in this reordered graph. My answer is that no, the result will not change because the GNN respects the permutational invariance. So it's a permutational invariant, meaning that the order of your graph, of your nodes doesn't matter. You can have any labeling nodes so long as you can internally you use a consistent representation of your graph. Right. So this is also a good question. So the other way around is very tricky in a sense. If you want to develop a neural network to predict a graph, then it's become tricky because the way you present, you have to label them in a certain order. Those nodes has to be ordered. Then you have to choose one adjacency matrix to learn. And there are equally like many variations of the representation, like as this question get asked, like you can always relabel those nodes and mathematically it become a different adjacency matrix, but they are same graph. So this composes a very difficult question in graph generations. I think this is still open question. I have seen some solutions to this problem, but they doesn't scale well in terms of producing large graph sizes. They can deal with like tens of nodes, 50 or even 100, but beyond that, it's very challenging to produce large graph size. I think it's a very challenging task. Not only machine learning, I think mathematical ground is also challenging. Yeah, this is a very good question.
Any other questions?
If not, maybe we just shout for some other venues you have, like in this conference. There are much more geometric learning topics in this conference. Graph neural network or geometric learning, they are the same things. This morning we had a section on the geometry deep learning, and I think we also have some regression on the graphs. And on Wednesday, there's another mini tutorial from DeepMind talk about the geometric learning. Here, people managed to put the connection between graph neural network and the PDE view, partial differential equation. See that graph convolutional layer is a form of partial differential equation. There are other like application of the GNN, like spectrum inspired GNN and learning with the graphs. Those are very interesting topics. And you can see the graph becomes popular because it's very powerful. The graph structure is very expressive. It can naturally represent many scientific data. Yeah, I will not go through all of them, but this could be a good example. Yeah, we have a new question.
Yeah, one.
Oh.
The graph level.
Right. Okay, another question. Any recommendation for graph level regression examples / papers / datasets? Most examples seen to be classification. That's a good question.
So the example in the slides for graph level, the typical graph level problem is related to molecular to predicting molecular properties, and there are several data sets available even in PyG, from like ranging from like smaller data sets to very large data sets, and even competitions. There is like these data sets, some of the molecular data sets are available on the OGB
Open graph benchmark
website.
Yeah.
And they are also available on a different, I'm pretty sure that if you Google it, predicting molecular properties, you can find these data sets. And then Shangyang can give you some examples from high energy physics.
Yes, we have many tasks that relate to graph level regression or classification. For example, one data set we should publish soon is to predict the property of a collision. So we use graph to represent a collision, and we want to determine what's the total energy of that collision event, or not the total energy, but the kinematics of top quarks get created in that event. That's like a regression task, because we are asking the graph neural network to predict the properties associated with the top quarks. Yeah, that I think there should be other like data sets open and a paper associated with that. If you are interested, I can send our paper to you for these examples.
I'd like to ask a question.
Yep.
Where do you see GNNs in business within like the next 5 years? Like an application. Yeah, business application. Yeah.
What?
So the question is, where do we see GNNs used in business? So one place where GNNs are used by social media is to make recommendations.
Yeah. Like, yeah, my major is in academic for the high energy physics. That's what I focus on. So I can not really comment on how the industry will use it. Yeah, it's out of my field.
Yeah, but like, so there are large models used by Facebook and Amazon in doing recommendations. They are really interested in developing these recommendation models with NVIDIA and.
I think LinkedIn that does that a lot. That they have a graph neural network that kind of like.
And in addition to that, self-driving cars, recognizing pedestrians or whatever, you have these sensors and LiDAR data. However, at this point, the GNNs, the inference of the GNN is slower than the inference of graph convolutional networks, so they are still in development for this type of applications. I think so. Some of other applications are related to identifying outliers in computer network traffic in order to identify intrusion. In terms of like time series and other type of tabular data sets, I've seen research that does impute missing data or imputation and forecasting. And there are other applications like mathematical and physical.
Yeah, I mean, at least there are some drawbacks of the GNN that the industry may also want to solve. Is it's not easy to train them, and they can be slow compared to MLPs. It's very hard to accelerate them because they have do the message passing, which have the random memory access that can be a challenge from a computational point of view. If you want to like embed it to have low latency cases, for example, self-driving car, you need a very fast model to respond.
So predicting the molecular, there is another question about graph level regression. So the molecular properties are not classification tasks, they are regression tasks. So it's like you actually predict the values of a function. It's like you predict a real numeric value, not a 0 or 1.
Yeah. I mean, what I'm saying, like, at least in one of my publication, we do the regression, just predict the top quark kinematics for a given event. That data set, I don't think we have published the data set yet, but that's in our goal to make them public. Right? I mean, in the end, classification, I view classification as a specific case of regression. In this case, you regress to 0 or 1. It's a bit cheating, but yeah. But if something like works for classification, I feel it can also work on the regression. From machine learning point of view, yeah, change the loss function. All right, we are very close. Yes. One last. Oh, sorry, missed it. Please. Oh, the question is asking why use GNN, not conventional algorithms. The current experiments are using conventional algorithms. The problem with the conventional algorithms is that, first of all, it's very hard to run them efficiently. They cannot take advantage of the development of the GPUs. We have a lot of people working on it to port the conventional algorithm into GPU so that they can run them in parallel. That's the ongoing work. And there are some attributes which GNN cannot replace. The accuracy or this uncertainty estimation from the conventional algorithms are required by the experiment. However, this kind of like once you get a track candidate, you get the track parameters. That step, conventional algorithm did a very good job. What conventional algorithm did not do good is to do the pattern recognition to get the track candidate. That's a combinatorial problem, and the conventional algorithm doesn't scale well. When you have more and more hits in your data, the time takes scales quadratically as a function of number of nodes. But in our study for the GNN, it scales almost linearly. So it will save you a lot of computational power. We are still on the stage of R&D to make the GNN more competitive than the, we are now like reach the same performance, but yet we are beat them in computation yet. Although GNN can run on the GPU, but as I said, GNN is actually slow, and we are speeding up the inference on using the graph neural network in order to compete with the conventional algorithm. Yeah. Mm-hmm.
Okay, thank you so much for coming. And as I mentioned at the beginning, we are part of the broader engagement program. There are other tutorials. Tomorrow there is a Julia tutorial. And if you are interested, please check the schedule to see some of the other activities related to the broader engagement program. Thank you so much.